In this video, I want to derive what's called the small signal model of a MOSFET, which is just the approximation of a MOSFET so that we can use linear circuit analysis. Before doing that, we want to look at this MOSFET and kind of analyze what its response looks like. So this one has two voltage sources. You can see there's an AC voltage source, and then we have these two DC voltage sources. So in order to figure out what the output is, we have to use superposition. So with superposition, we can analyze the AC and DC parts separate. So we're going to start with our DC analysis. So if I redraw this circuit for the DC analysis, we're basically turning the AC voltage source off. So we end up getting this is what our circuit will look like. So here's our transistor, and then we just have our bias voltage, which is 1.8 volts. And so then when I solve all of this, you see this is going to be inactive. And so then we are going to have that ID is equal to 1/2 Kp VGS minus VTO squared. If I plug in all of the numbers, I get 1/2 0.17, and then the VGS is just my bias voltage, 1.8 minus 1.6 squared is my ID. So if I solve this equation, I get a current of 3.4 milliamps. And then if I wanted to, I can solve for my V out right here. And so my V out is equal to 9 minus 3.4 milliamp times 1 kiloohm. So we do all that, and that comes out to 5.6 volts. Okay, so now we're going to do our AC analysis. So in the AC analysis, we are going to turn off our DC voltage sources and only have our AC voltage source. So we're going to have, this is going to be my V in, and this is going to be my gate. And then my transistor is going to be a current source. So it's going to have a value of GM times VGS. This right here is my source, which we're going to ground. And then this is my resistor. And then on the top, it's going to become ground. And it's going to look like that. So, but we don't want this ground going up in the top. So we're going to take this and we're going to flip it down like this. So this is going to be my 1 kiloohm, and then this is going to be my out. And so you can kind of see that this current kind of gets pulled around like this. So this is plus minus right there. So then if I solve this, we see that my V of out is going to be equal to 1 minus 1,000, because my current's going up, times the GM times my VGS. And the VGS in this case is just my V in. So then if I look at the GM, my GM is going to be equal to my change in current relative to my change in voltage. So now we can just go over to LT-Spice and we can just kind of see what this does. So if I run this and we measure the current right here, you see that this is producing a current of 0.6 milliamps. So this is equal to 0.6 milliamps over 20 millivolts, which is equal to 0.03 amps per volt. So then if we put it all together, the V of my out is equal to minus 1,000 times 0.03 times my V in, which was 10 times 10 to the minus 3 times the sine of omega t. So now when we put it all together, we see that my total V out is equal to the 5.6 minus, and then we put all these together and we get 0.3 sine of omega t. So you see we have this AC part that's basically riding on this 5.6 volts. So if I were to plot this whole thing, you're going to see this is going to be my 5.6, and then I'm just going to have my little sine wave sitting right on top of there. Okay, so this is kind of how it works, but now what we want to do is we want to derive these as equations. And so what is GM in terms of equation rather than having to use LT spice in order to do it? So we're going to start by looking at my MOSFET. So with this MOSFET, what we're trying to do is we're going to take and we're going to figure out how does the current change. So I'm going to come in here and we're going to delete this off and just kind of create a variation here. And so we're going to make this to be a pulse. This is going to be from my cutoff to about 1.9. And so now if I run this and look at the current and do this as a function of my, called this node GS, then you see that this is kind of sweeping up. So if we're just going to make this a little smaller. And I'm just going to copy this over. So this is my current through my transistor as a function of the voltage. And what we're really doing here is we're picking some operating point. So in our operating point right here, you see it's going to produce a specific current. Now around that, I'm going to have a range of voltages, and that's going to produce a range of currents. So you see what ends up happening is if I have a voltage that looks like that, that's going to produce a current that looks like that. Now in order to do that, you see that that's going to be a function of this line right here. So I'm going to take my operating point and I'm going to fit it to a line. And so the slope of that line is basically going to be the derivative of my current. So what I'm going to do is before we had GM was equal to delta ID over delta VGS. And so then this is going to be equal to the derivative with respect to VGS of my current right there. So now we can just plug in, we know we're in active. So my ID is equal to 1/2 Kp VGS minus VTO squared, and I'm going to take the derivative. So the derivative of ID with respect to my VGS, which is going to be equal to Kp times VGS minus VTO. So you see that the 2's square off and we get that. And so this is equal to my GM. So there is the GM that I created. And so now whenever I see my transistor, this is my drain, this is my source, and this is my gate, I can take this and I can replace it with a model that looks like this. So this is my gate, and then this is my GM VGS, this is my source, and this is my drain. So I can basically replace my transistor with this dependent current source model. Now we want to add in a little bit more fidelity into this, and so in order to do that, we're going to look and see how it changes with respect to the D and the S. So we're going to come in here and we're going to add in a resistor, which is often called RO, which is going to be related to how my current changes with respect to my VDS. So in this case, we're going to a little bit more accurate current model. And so then this is equal to 1/2 Kp VGS minus VTO squared. But then I have this 1 plus lambda VDS. And if I want to know what this looks like, we see that I have as a function of VDS and ID, I get something that looks like this. And so you see it has a little bit of slope on that line. And so even though we're inactive, it has a little bit of slope, and then that's going to be related to the lambda. So now we are going to go RO is going to be delta VDS over delta ID, which is going to be equal to the derivative of ID with respect to VDS, and then we're just going to flip that. Okay, so then I'm taking the derivative of ID with respect to VGS is going to be equal to 1/2 VGS minus VTO squared times lambda. And so now my RO is going to be 1 over 1/2 VGS minus VTO squared lambda, which is approximately equal to 1 over ID lambda. And this is equal to the RO. Okay, so now we have all this. So the GM equation is right here. The RO equation is right here. And then every time I get my MOSFET, I replace it with this model, and then I can solve it. So